Hello, Ryan, you can see my slide? Apa Nadia? Nampak slide aku tak?
Nampak, Doktor.
Ada dengar bunyi bising tak?
Tak ada.
Tak ada bunyi kipas. Anda dah ada slide ni belum? Chapter 6, 8 dengan 10. Dah ada ya? Hello? Dah ada belum slide ni?
Dah, Doktor. Dah.
Dah, okey. Okay, now at 2. Can we start now? Buat je minit. Hello, Assalamualaikum.
Salam, Doktor. Salam, Doktor.
Can we start now? 30, 41, 10. Okay, I will start, okay? Okay, Assalamualaikum. Selamat tengah hari. Good afternoon. This is chapter 6, okay? Chapter 6 will be included in test 2. Okay, so three questions for one for chapter 4, and then chapter 5, one for chapter 5, and then one for chapter 6. 3 questions for test 2. Okay. Let's start. What is the objective? After you study chapter 6, what can you get? Okay, this is about multiple ration. Okay, from chapter 1 to chapter 5, you studied about the just single ration. Okay, this is multiple ration. Okay, so you have many number of ration. That is multiple ration. The objective, you can define different types of selectivity and yield. Okay, we study about the selectivity and yield. Selectivity is about the product, yield also about the product. Okay, and then you can choose a reaction system that would maximize the selectivity of the desired product given the rate loss for all the reactions occurring in the system. And then you can describe the algorithm used to design reactors for multiple reaction. And then as usual, you can size the reactors to maximize the selectivity and also to determine the species concentration, whether in batch, semi-batch or CSCR or PFR or PBR. Okay, here you will study a little bit about the semi-batch. Okay, the last objective is for the polymath. Okay, the Tahaja will give you we have 13 groups, so the Tahaja will give 13 questions, I think, for our class. She said she will give us this week. Okay, I will forward to you. And then that's the objective. Nak pergi ni. Okay. This is type of multiplication. Okay, what is multiplication? We have many types of multiplication. For example, series ration. You can see like electric circuit. This is series. Okay, series ration. A react to produce B, and then B react to produce C in series. So this is, we call it series reaction. The K1, K2 is the constant. And then parallel reaction, we also have parallel reaction. Parallel reaction, you can see from the same reactant, you can produce many types or more than one types of products. We call it parallel reaction. For example, A produce B at the same time in the same reactor. A also produce C. Or you can write like this: A, then arrow B, and then arrow C. Okay, you can write like that also. And then we also have complex reaction, mix of the series and parallel reaction. You can see this is parallel reaction, right? This is the equation 1, this is the equation 2, or this is the reaction 1, this is the reaction 2. You can see, you can imagine this is on this is in one reactor. So A will produce B plus C, and at the same time, when the B produce, the A will react with C to produce D. This is what we call it complex reaction. Okay. And then independent reaction. This also can be occurred in the same batch reactor, in the same reactor. Okay. We call independent reactor. A produce to C, and then at the same time, when we put B in the same reactor, can produce D, but do not touch or do not disturb the other reaction. This is also can be occurred, okay, in the same reaction. This is type of multiple reaction, but usually in test or exam, maybe number 1 or number 2, okay? Yeah, usually number 1, number 2. Okay, this is about what is selectivity and what is yield, okay, from now. Selectivity is about the product, okay. For example, A produce D and U, okay. D is desired product, U is undesired product. So when we are talking about the selectivity, just about the D and U. The total of D and U must be 100%, okay? So maybe this is 60%, this is 40%, or maybe 80%, this could desired, and 80%, and then maybe 20%. So selectivity is just about the product. So the total must be 100%. And then the yield, how to calculate the yield? The yield you must calculate based on, usually based on the reactant, okay? For example, D, the maybe in gram, maybe you get the D in gram, and then you D over A, and then times 100, so you can get the yield. Yield is about the ratio of the product to the reactant starting material, and then times 100%. Okay, usually in percentage, this one. Okay, this is what, this is just to show you the, this is A, starting material. So you have D and you have U. You have desired product and you have the undesired product. So you put the A in the reactor system, and then because you want the D, you have to separate the D from the U by the separator. Okay. This is just to show you the efficiency of a reactor system. Okay, this is a graph. Y-axis is about cost, about money. And then this is low or high. So just to show you, if you have the cheap, which one? Cheap reactor, you have to buy expensive separator to separate the products. Okay. And then in contrast, if you have expensive reactor, you just have to buy a cheap separator. okay, to separate both of the products. Okay, this is the how to calculate the selectivity. We have two, instantaneous and also overall. Okay, you can see this is bar. Okay, SDU. What is the meaning of SDU? D, the selectivity of D compared to the U undesired product. Okay, SDU equal, we can calculate based on the rate. Okay, rate of reaction RD over RU. And this also we can calculate from that. This is flow. Okay, flow desired product over undesired product. Okay, but the yield, you can see the yield. This is the about as I said, the selectivity just about the products, but the yield we have to relate with the static material. That's why YD equal RD over negative RA, the rate for the static material. Okay, negative RA. This one is the YD for the overall. FD, this is overall. So FA naught minus FA. Okay. Also yield. So based on the static material. Okay, instantaneous selectivity SDU. Same. RD over RU, rate of formation of D over rate of formation of U. And then selectivity, overall selectivity, exit molar flow rate of desired product over exit molar flow rate of undesired product. Okay, undesired product. So this one minus this one. No, just undesired product. Okay, this is for yield. So this is for batch system, SDU, batch system. As usual, you use N. Okay, and number of moles. Okay, and then this is also number of moles. But the flow system, no, this one. This is for the batch system. No, for the flow system. No, for the flow system. Flow system is this one. Okay. You use flow rate, not the number of mole. Number of mole is just for the batch system. Okay, this is parallelization, parallel reaction. Okay, parallel reaction. Example 1. Okay, you can see A produce D, desired product. At the same time, A also produce U, undesired product. So if we're talking about the RD equal KD, this one, CA alpha 1, okay, power of alpha 1, okay. Let's RD equal KD CA power of alpha 1. And then let's RU equal KU CA power of alpha 2. This is rate loss, okay. Rate law for the desired and undesired product, okay. So if we, so the overall RA is equal RD plus RU, okay. This is the total because we have the same starting material. So the negative RA, the total rate must be RD plus RU. So because RD is here and then RU is here, so become like this. Okay. So when you calculate the SDU, SDU is RD over RU. So this one over this one. So will be like this. KD over KU because of over, okay, CA alpha 1 minus alpha 2. This is what we call instantaneous selectivity. Can you understand? Hello.
Yes, doctor.
Okay. Go next. Okay. Okay, how to maximize the selectivity for one reactant? Okay, for parallel reaction. This is we call it one reactant. Okay, same like before. At the same time, A will produce D desired product and also undesired product. So we know now that the SDU is equal this one. Okay, from this one, right? Okay, we know this one. So there is 4 cases, okay? How to maximize the selectivity for one reactant, okay? For case 1, for example, if the alpha 1 is larger than alpha 2, so to be easier, they simplify the alpha 1 minus alpha 2 as an A, okay? Which is A is a positive number, okay? So from this one, we can get this one. Can you accept? Because SDU equal RD over RU. KD over KU, CA alpha 1 minus alpha 2, which is A. So become like this. Can you understand? Okay. So if you are okay, and then you see this, just see for this equation, this one and this one. So you want to maximize the selectivity. So you want to maximize the SDU, okay? Selectivity desired product over undesired product. So how to maximize this one? Just follow the simple equation. If you want the S is large or big, so what will be happen here? The CA over the CA power of A, small a, is over 1, okay? So if you want the S larger, so the CA must be larger or small?
Larger.
Dia berkada terus, okay? So how to keep the CA larger? So Ca is the concentration of A, okay? The concentration of the reactant. So how to keep the A is larger? You have to keep the concentration of A as high as possible. How? There is two cases. One is gas phase reaction, one is liquid phase reaction. So in gas phase reaction, you have to run it without inerts, because inert, what is inerts? Inerts may be helium, maybe nitrogen, maybe argon, something like that. So you want the Ca big end. So please or do run without inerts, or with inert if cannot go the reaction, if the reaction cannot go without inert, just put a low concentration of inert, and then make it the Ca keep high, okay? High pressure also one of the way how to keep the Ca high, okay? You know P equals CRT. If you want the C higher, so the P must be high kan? P equals CRT. Hello.
Yes, doctor.
Yes, doctor.
Yes, PV equal nRT, N over V equals C. So P equals CRT. So if you want the C higher, the pressure must be higher. That is for the gas phase, okay? Run without inert or a small amount of inerts. And then for the liquid phase, use the use of diluent should be kept to a minimum, okay? For the liquid phase, sometimes and all times, I think you cannot run the reaction without the diluent or solvent, okay? So if you want the Ca, the concentration of A is high, just use small amount, okay? Keep to a minimum amount of diluent. So you have to remember, in test or in final exam, you will have this one, okay? SDU, you will give the rate, okay? The rate like this, the rate of reaction, okay? and then they will ask you how to maximize the selectivity, and then you will calculate, okay, like this. And then when you get the CA is at the top, you have to I can say copy and paste this one, okay. You have to answer like this, okay. And then other than concentration and also pressure, what we can adjust, we can choose the type of reactor, okay. So just remember, if you want this reactant to be high concentration, in high concentration, you have to use the batch or plug flow reactor, okay, instead of CSTR. Okay, just remember. Next, you will use CSTR for the lower, you can see. Okay, for the high concentration, use batch or plug flow reactor. Okay, we will go case 2, okay. Oh, case 2, okay. This one is when the alpha 1 smaller than alpha 2. You can see this, the case 1 is alpha 1 larger than alpha 2. Now is alpha 1 smaller than alpha 2, okay. Same equation, same calculation, very simple. So when you want the S to be maximized as du, so you just put this one is alpha 1 minus alpha 2 is equal A, right? So RD over RU become like this. So now the A at the bottom, okay? You can see. So when you, this is berkadar sungsang, okay? When you want the S larger, the A must be smaller. How to get the CA smaller? This one. So the contrast, in contrast of the case 1, okay? So the concentration of A should be lower as possible, okay? How to lower the concentration of A? If you in the gas reaction, you use inert, okay, more inert, and then when the liquid reaction, you use more diluent or more solvent, okay, then you can get this lower concentration of A, okay. Run it at low concentration of A, okay. Same like this, you adjust the concentration. And then concentration, we have two, gas and liquid, and then you choose the reactor. So for the lower concentration, usually they use CSTR to maintain the concentration of A at low level, okay. You also can use a recycle reactor. I do not have here, ada gambar kat sini tak ada. This one, this one bukan. Like this one, okay. This is a recycle reactor, okay. You use this is the for example, just A. Think about just A. A is the product. Go like this, and then you can get the desired and undesired product. And the undesired may be the solvent. So this solvent can be recycled back, okay. Then that is what they call it. Mana tadi? You use a recycle reactor. I forgot the page number in textbook. There is one page showing the apa the type of reactors. So you can see that I think chapter 6. You can search in textbook. You can see the recycle reactor. I suggest you to use to sketch. When you get the chapter 6 question for chapter 6, I suggest you sketch the type of reactors, okay, to get the apa, to get more to get marks. You draw the recycle reactor in which the product stream acts as a diluent to maintain the entering concentration A at a low value. Like I said here, one of the product or undesired product is diluent or solvent, and then you can recycle back. So if you know about the reflux refluxation, you use the condenser, maybe also you can see the recycle recycle reactor. Okay, this one. Okay, diluent, you get back the diluent, and then recycle lah, recycle. Okay, this is when you get the Ca at the bottom. Okay, so you have to write like this. One is about the concentration itself, and then about the apa nama dia, type of reactors. Okay, and then this is we will go for case 3 and case 4. This is all about the K. What is K? Constant, rate constant. Okay, this is about rate constant. Sensitivity of the rate selectivity parameter to temperature can be determined from the ratio of the specific reaction rates. Okay, so if you want to maximize the HDU, you can also adjust the temperature based on the rates reaction rate constant here. So the HDU equal KD over KU. This is the Arrhenius equation. If you apa uh, can if you don't apa, you still remember the Arrhenius equation? We have A, we have activation energy, we have over RT, right? This is activation energy. Okay, when you do like this, KD over KU, you will get this one. Okay, which is A is frequency reactor, E is activation energy, D is the desired product, U is undesired product. So you will adjust the temperature to get the HDU maximum. Okay. For example, case 3. Okay. Okay. You know this one, eh? This one is from this one is from here, eh? Okay, from here. This one. Okay. Case 3, when ED larger than EU. Okay, ED larger than EU, what happened? Okay, ED larger than EU, KD or RD will increase more rapidly with increasing temperature than does KU. Okay, then the reaction system should be operated at highest possible temperature to maximize the SDU. So if the ED is larger than EU, you have to increase the temperature as high as you can. Okay, and then in contrast for case 4, when the EU or larger than ED, in contrast, right? So you have to lower the temperature. But you have to remember, the reaction should be carried out at low temperature to maximize HDU, but not so low that the desired reaction does not proceed to any significant extent. You have to know there is a limitation in temperature for the reaction to be occurred, right? So you can reduce the temperature, but with the limitation, not so low. Okay, and then if so low, the reaction cannot be occurred. Okay, so this is about the how to maximize the, there is 4 case, how to maximize the selectivity of the desired product to the undesired product. So you will get the, you will calculate the S. Okay, they will give you the RA rate of reaction or rate law. They will give you rate law, and then you will calculate, and then you will see if the case is apa, like this, A at the top, what happened, and then at A at the bottom, what happened. This one is just control the concentration, the pressure, and then choose the best reactor. Okay, and this one you also can adjust the temperature. That is the how to maximize the selectivity for parallel session uh, for one reactor. Okay, and then this is for two reactants. Okay, if you have two reactants, for example A plus B, you have desired and undesired product. What happened? Similar like the previous one. At this time, Rd equal K1 Ca power of alpha 1, Kb beta 1. And then Ru is Ku Ca alpha 2, Cb beta 2. Okay? When you calculate for the SDU is equal Rd over Ru. So become like this. Rd over Ru, K1 over K2 Ca alpha 1 minus alpha 2 Cb beta 1 minus beta 2. So if you simplify, okay, figure 6.3, I forgot. I think that one, figure 6.3 in the textbook that you can see all the type of reactors. Okay, so, okay, now you have this one, okay, for two reactants, A and B. So how to minimize unwanted products for two reactants? Minimize unwanted reactant is same with the maximize desired product. Okay. So case one, when the alpha one larger than alpha two, beta one larger than beta two. Okay. Let's use the same alpha one minus alpha two equal A, beta one minus beta two equal B. Okay. So case one, when this larger, you get this one. Okay, SU equal K1, K2, Ca power of A, Cb power of B. So you just see this one and this one. How to maximize this one? You have to maximize this one, right? So how to maximize this one? Now you have two reactants, not just one reactant, okay? When two reactant, this is a we touch the semi-batch reactor, okay? Okay, so to maximize the SDU, we have to maintain the concentration of A and B as high as possible. So that's for the concentration. How? We will choose this kind of reactors. One is tubular reactor, in which you put the A and B at the same time, and then batch reactor also you can put the A and B at the same time with the high concentration. And also for gas reaction, you can, because you want C higher, so you use the high pressure, P equals CRP. And also you reduce the inert. Okay, all is, you can see all is same. Okay, adjust the concentration, adjust the pressure, adjust the concentration, reactant and also inert, and then or diluent for the liquidation. Then you choose the appropriate reactor. Okay, and then case B, what happens when alpha 1 larger than alpha 2, beta 1 smaller than beta 2. Okay, now you have SDU equal K1 Ca over alpha over K2 Cb by power of B. Okay, this is A, this is B. Okay, now to maximize this one, you the Ca is the top, the Cb is the bottom. You have to make it maximize higher the Ca, and then the B make it lower. So how? Okay, to maximize SDU, make the concentration of A as high and concentration of B low. Okay, how to achieve this one? Okay, this is what we call it semi-batch reactor. You can see batch, okay, but semi, separuh. Okay, batch is batch, and then how to keep the A at high concentration and B at lower concentration, you have to put the A at the first one, you have to put the A in the reactor, and then you drop wise, put the B drop wise, and titik by titik, okay, drop wise, sedikit demi sedikit, you put the B, okay, then you can keep the B in lower concentration, okay. If you get if you calculate the SDU, the rate of reaction, you get like this, 2 reactant, and then one is you have to keep it higher and one to keep it lower, so you draw this one, okay. Or you use the tubular reactor with side stream. You can see the A is higher, you just put A here, but the B is this side, okay, side, you put slowly, okay. Or you use a series of small CSTR, okay, which is A you put here, but B you put one by one in each reactor like this. So if you get this one, you have to draw like this. You have to put which is B, which is A, which is B. You have to draw like this. Okay, that is for the answer for the chapter 6. And then this is the when both are at the bottom. So to SDU maximum, you keep the CA and CB lower. How? You use the CSCR. Okay, if you can remember the case 2 for the one reactant, use CSCR when you want to keep the the concentration, low concentration, use the CSCR. Or use the tubular reactor with a large recycle ratio like this, okay, can recycle, and then you can feed diluted with inert, okay, inert or diluent for the liquid ration, and then low pressure, okay, P equals CRT. If you want C lower, the P must be lower if for the gas ration. And then next, case 4. Case 4 is the apa? Terbalik daripada case 2, okay? Now CB is at the top, CA is at the bottom. So CB must be higher, so you just change CB higher, so put at the beginning CB here, and then drop wise the CA at the A, okay? We can keep it lower in concentration. Then this is also just change the P and A, okay? Same with case, similar to case 2, but change the A and B, okay? Then, okay, that's all about them, about them parallel ration, okay? Okay, in parallel ration, the undesired product could be minimized or the desired product could be maximized by adjusting the ration condition, okay, the concentration, the pressure, the temperature, okay, that is for the parallel ration. And then another one is you choose the proper reactor, okay. For example, CSTR for the lower, okay, you have to remember this one all. That is for the parallel ration, whether one reactant or two reactants, okay. But for the series ration, the most important variable is time. You do not play with the concentration, you do not play with the ration condition, you do not play with the reactor type. But for the series ration, for example, A produce B and then B produce C. If your B is a desired product, you have to play with the time. You have to know when the maximum time, when the time B is maximum. Okay, so at that time you have to get the B. Okay, and because when you prolong the time, all the B will convert to C, and then if the C is undesired product, you cannot get your desired product. Okay, so you play with time, which one you want. If C, your desired product, is no problem, you just leave the ration, but at the end you can take the C. But if the B is the desired product, you have to play with the time, which is flow rate is a space time, and batch rate is a real time. So there is an example in textbook regarding this series ration. Sometimes they want you to calculate the maximum time for the B. Okay, I think in your, you can see, please study from your textbook. There is also past year's question, I think from Dr. Hajar, is regarding the maximum, how to calculate this one. Okay, the tau, this is T or the tau. Okay, that is for the, okay, if you do, okay, your assignment next week, I want to see one of your question is from this what I said, that you determine the tau. Okay, from the graph, and then lastly you have to plot the graph. Okay, I want to see you have 13 groups, so one group you should search for that question. Okay, and then this is our algorithm for solution to complex multiple ration. You cannot, this is not for your exam, I think for your assignment, because you see here, combine, polymath will combine for you. You cannot calculate in test, okay, because you do not have polymath to calculate for you in test or exam. But the algorithm is same, okay, for multiple or complex ration. Same with the single ration, you have more balance, you have 4 kan, batch, CSTR, PFR, PBR, okay, more balance of each species, and then you have to know the rate law. In chapter 6, the rate law is a net rate, okay, net rate of the ration, because you have many ration. So if the rate in the ration 1 and in the ration 2, you have A, both ration you have A, you have to combine. That is, we call it a net rate of ration for each species. For example, RA equals sum of all the RIA. I is the number of ration. Okay, if you have 2 rations, so R1 A is about the A in the first ration, and then sorry, and then R2A is the A in the second ration. Okay, okay, we will see later. Okay, and then you have the stoichiometric, whether the liquid or the gas phase. The liquid, you do not have to use the epsilon, but the gas phase you have to use the epsilon. This is maybe you, if you cannot remember, this is for the other than the other than conversion. Okay, the C in terms of other than conversion. We do not have the X here. Okay, and then the polymer will combine for you. Okay, this is the mole balance. Okay, same, but we do not touch for the semi batch. Okay, we just put touch for the batch, CSR, PFR, and PBR. This all you know, sir. The net, not the net, the ration rates in here, in the above more balance are net rates. Okay, all this one is net rates. What is net rates? Okay, 44, another 5 minutes. Okay, net rates operation. Okay, let's consider Q number of reactions. Okay, so you have reaction 1, reaction 2, reaction 3, reaction 4 until reaction Q. So you can see each reaction we have A plus B to C, 3C plus D, A plus 2C to B, and so on. Okay, and then jadi pula. So net rates of, for example, net rates of reaction A and B. Okay, for A and B, RA is what? Just the reaction which has A. Okay, so we have A here, R1A. Okay, we have A here, R2A. Okay, reaction number 2. We have 3A here. How about 3A? Hello? We have A in 3, in reaction 3? No. No, we have no A in reaction 3. So the R3A equals 0. Okay, we not forget it. And then RQ we have A. So RQA. So you have to plus all this. Okay, add all this one, the total is the RA, net rate, what we call it, that is the net rate of RA. Also RB, okay? RB we can see R1B we have 1B, but no, R2B is 0. Okay, we do not have B. R3B we have, QB, okay, we have. So that's the meaning of R net rates, okay? How to calculate the net rate? If you can remember, RJ equal, this one is same. RJ is the I sum of the RJ, okay? If you can remember this one, what is this? This is the relative rates of reaction. So you will use this one, okay, to calculate all this one. Okay. For example, this is the general one. This is the negative because of the reactant. Positive because of the product. You have R1A, IA, IB, IC, ID, okay? For example, okay? You have example liquid phase ration. You have liquid phase ration, and the equation 1, the ration 1 is like this, A plus 2B equals C. And then they gave you the negative R1A equal this one. The specific ration rate K1A is defined with respect to species A. And then ration 2. Ration 2, they just give you negative R2C. You see? R2C, not R2A, not R2B, not R2D, but they give you the negative R2C equal this one. So this one, case 1 is for the PFR. So the mole balance is like this, okay? And then you know, you have to use this one. Okay? It's very simple. So RA, you just have two ration. So the RA equal A in the first ration, A in the second ration. So this is the first ration. This is for the second ration. You can see this is when you use change to like this, R1A equal 1N. Negative, negative because reactant. And then RB also negative because reactant B over 2. See, so you can get like this. So you know now A equal this one. You use this one, okay? R1A equal K1 negative K1A CA CB power of 2. Where you get it? This one? You get from here, okay? They give you negative R1A equal R1A CA CB power of 2. Okay? Okay, and then this one is for the reaction 2. Okay, this is about the C and A. Okay, not about D, C and A, because for this one they give you the negative R to C, so you have to relate with the R to C. R to C is here, so you can get the R to A equal this one equal this one. So RA is the R1A plus R2A. You can get this one. Can you understand? Hello.
Yes, doctor.
Okay. Okay. And then same goes to the species B, species C, species D. Okay. You have to get the net rates of the RB, RC, RD. And then you go with the stoichiometry as before for the liquid, for example, like this, and then you combine. This is for the PFR, and then you can get the RA like this. You just kembangkan dia untuk dapatkan ni. Okay? And then this is for special species D. And then polymath will like this. Okay? Calculate for you. I don't know. I think Dr. Haja give this kind of assignment. This is you can see. You can read by study by yourself. This is just net rate, how to how to write the net rates. Same. Okay. Maybe this is the polymath. This is for the polymath, but one time previously and Dr. Haja had a question before you combine with the one before you combine with the polymath. So Dr. Haja can ask you until here, okay? Until this stage. Okay, this you can calculate, but they can ask you until this stage how to get this one. You got what I mean? Easy. You just follow the algorithm. Okay, this is for the liquid phase ration. Okay, this is for the CSTR. So you have to use the CSTR punya model equation. Okay, then all the same. Okay, this semi-batch not included. And then this is for polymath. This is a gas phase ration for the PFR. You can see this is you can see from the textbook the C in terms of other than conversion. Okay, you do not see the X. Okay, all the same. This is all the same. You just have to get the RA, then put in the Morbidden equation. Okay, the RA or RB, RC must be net rates. Okay, this is the example. Maybe one of your group can explain, can answer this one, and then oh no, this is the what's wrong with the solution kan? Cannot. Okay, this one. Okay, you can choose this one and then the other one. This is from Dr. Umi Aisha. Previously, okay. That's all for the chapter 6. Okay, it's about the multiple ration. Will include in test 2 and also in final exam. Okay, please study the previous and also the question from the textbook, from the CD, from the Fogler website. Okay, any question? See you next week on Sunday with the question. Okay, with the assignment. Any question? No question again. Stop sharing. You have the notes, right? For chapter 6, chapter 8, and chapter 10, all.
Yes, doctor.
Yes, doctor.
Okay. Any question? Can you understand what is the chapter? Ambil jadi okay, ambil surang je tu. What is the chapter 6 all about? Can you understand? There is a multiplication. Complicated, but there is the question for the chapter 6 in your test 2 and also in your final exam. Okay. Okay. I still not mark your chapter test 1 sorry. Okay, if no question, we can leave now. Bye bye. See you next week on Sunday.
Thank you, doctor.
Welcome.